All right. Before I go ahead with the titration, a little bit of everything that we have done in this chapter. This was acid alkalis in titrations chapter. We started off with a pair scale. We came to know it works from 0 to 14, all the way from acidic to neutral to alkaline or basic. We discussed about a few different solutions and their pH values, or how to measure the pH values, how a universal indicator works, how pH meter works, and we discussed different types of indicators and their color changes in acidic medium, alkaline medium. On top of this, I told you what the neutral medium looks like. Then we discussed acids in specific, or how they behave, or how hydrogen ion uh, acids give hydrogen ions in solutions. So that's how we define them too. Bases, on the other hand, can be divided into two categories: the insoluble ones and the soluble ones. The ones that are soluble in water, we call them alkalis. Alkalis give hydroxide or OH negative ions in the solution. We discussed them in detail too. Then we discussed how bases and alkali react with acids, and we call it a neutralization reaction. And we then came to know that usually, whether it's a base or it's an alkali, upon reaction with acid, it produces salt and water. So the same thing was occurring in case of acids, in case of bases, or in case of alkalis. We took the spectator ions out, which were the salt ions. We came to know that the equation is really about formation of water as a neutral product. And if you see this equation, this water is formed by the H positive ions coming out of an acid and OH negative ions, which are a characteristic of an alkali. So that's how water forms. So this clarifies that how the neutralization reaction produces water. But when we do that neutralization reaction in lab with an alkali and an acid, we call it a titration. This is what we are supposed to start with today. So in titration, we're going to follow the course of a neutralization reaction between an acid and an alkali, and it can be used qualitatively or quantitatively. Most importantly, we're going to use it quantitatively. Quantitative means how much of acid or how much of alkali reacts within certain volume of the other one. For example, if you say you have 25 cubic centimeter of an acid, then you can really identify in neutralization how many cubic centimeters of an alkali is required. So for this type of work in which the quantity of alkali can be found out, we call it a quantitative analysis, and this quantitative analysis is titration. So let's take an idea how this titration is carried out. There are a lot of diagrams on the next page, and they tell us step by step how this is going to go. What we are going to do is that we're going to follow this map, and apart from this map, there are a few things that I want you to note down. So it's better if you have the hard copy of your book in front of you, this page open, and you also have a pencil in hand. If you're not
Mhm.
ready, let me know when you are ready, because I'm going to ask you to write a few things.
Yeah, yeah, sir, you can see.
Take your time, I can wait. Since you're ready, let's get started. Now, you are going to see and get familiar with many pieces of equipment that we commonly use in lab in titration. But apart from how we are going to use a specific piece of utensil or equipment in lab, or apart from the fact how it works, we are going to understand a few certain things as a part of some specific hard and fast rules for the lab, which is really going to help you with your answers, the formation of answers, or how a certain experiment or a practical activity goes. Now, what you can see in front of yourself is a beaker in the first part, a pipette, then a pipette being used in a flask. Then you have a burette, which is actually clamped to a stand. And then there is another beaker. Apart from that, if I move with the help of the arrow, you can see the same clamp and stand, the burette, the flask, the same thing. And the material that was in the flask changes color. Now, before we move on to the actual steps, let me clarify something that most accurate pieces of equipment that we use in lab are two. Number one, that is burette and pipette. So whenever your work is about accuracy, accuracy of finding out how much volume is used, you're going to prefer these.
Mm-hmm.
If I talk about something that is medium accurate or moderately accurate or something that lies in between, I am going to put measuring cylinder. Though it's not drawn in all of these drawings, but measuring cylinder is the second most accurate piece of equipment. And when we talk about the least accurate ones, and mostly these are used for higher, bigger volumes, that's why they are least accurate. And I would rather write beakers, and I would rather mention flasks, right?
Mm-hmm.
Now, I am also going to give you a general idea that now these statements seem very confusing, so let's clarify. Beakers are wide mouth, right? That's why they are least accurate. They're only
Mm-hmm.
used to fill up major parts of volumes, higher volumes, bigger volumes. Beakers are commonly used for 50 cubic centimeter, 100 cubic centimeter, 250 cubic centimeter, 500 cubic centimeter, and even bigger volume. 1 liter, 1.5 liters. Beakers are there in the lab to transfer the aqueous solutions from one place to another, or to transfer liquid from one place to another. It is mainly for transportation from here to here, right? So
Mm-hmm.
it does not concern accuracy, though there are readings on top of a beaker, but it's not accurate enough. Okay. So
Yeah.
it gives us the idea that wider the mouth of your uh, utensil or equipment is, the more uh, the less accurate the utensil is going to be. Since beaker is like that, since flask's mouth may not be wider, this is to avoid splashes, but the actual readings are given at the point, and these are definitely, since they're wider, flasks are also least accurate. Measuring cylinders, on the other hand, look like this. Since the mouth is not wide enough, since the whole portion is not wide enough, flasks are too wide, beakers are too wide, not just the mouth, the whole thing. So they are least accurate, they are more accurate. And take a look at this pipette. Take a look at this burette, how less wide they are. That's why these two are the most accurate piece of equipment. Since the mouths are too less wide and there are too many readings, they're a bit longer structures, they're very accurate. But as I do understand they're accurate, they can hold very less amount of liquids or solutions. You'd notice the capacity is this. For burettes, the usual capacity is this that you're going to use in lab. You're also
Mm-hmm.
going to get pipettes, their usual capacity would be just this. This is too less. Flasks, beakers, measuring cylinders work with bigger volumes, why they are less accurate. So this whole idea of accuracy is given to students so as they would understand whenever they are writing on a piece of experiment, if the experiment is about accuracy, what should they pick? So if you want to be more accurate, try going with these. If you want to be less accurate and you simply want to transfer the solution from one point to another, try using these. If you want to transfer the solution as well as you would like to be a little bit accurate, if not completely accurate, prefer this, something in between.
Mm-hmm.
Okay, now
Yeah.
let's get started. Oh, my bad. Let's get started. And I'm gonna erase a few things. I'm gonna make a little bit more space, right? So What we do is that we start out with measuring 25 cubic centimeter of hydrochloric acid using a pipette and a pipette filler. This is a pipette. The central portion is made a little bit wider so that it can actually hold a little bit of amount. If we don't do that, 25 cubic centimeter would become a little bit of a problem, or the structure would be too lengthened, right? They are not going to ask questions about these. This is for your own basic idea. Okay,
Mhm.
so we take it out of a beaker. We measure exactly 25 cubic centimeter. The good part about the pipette is that pipette can exactly measure in this whole of its structure a specific amount of a liquid. So if you're supposed to measure out one specific amount of liquid, that is the entirety of the pipette itself, it's a great tool to work with. Moving on, you transfer the entire content. Notice the pipette is filled from the very bottom all the way to the very top, like I mentioned, from the top to bottom. I should have mentioned over here, not here. Okay.
Mhm.
So transfer it to a conical flask. Remember, conical flasks have a less wide mouth but a wider bottom to make sure that we can put larger volumes. But when we try to shake them sideways, they don't spill out because they have a less wide mouth. This is just to make sure that there must be no accidents in lab. That's why we prefer flasks, because they don't spill stuff or they don't splash stuff like easily a beaker would do. Flask won't. So we also choose a beaker and fill the puree with sodium hydroxide solution. So we have acid over here, notice, and we have alkali over here. All right. Take the initial reading of the burette, recorded to two decimal places. Burette can be recorded up to two decimal places, which means the reading can be 10.15, right?
Mhm.
So burettes are very accurate. This gives you the idea. Up to two decimal places means it's really accurate. Now, beaker, if you're not successful with pouring with the beaker directly into a burette, you may put a flask over here, a funnel over here. My bad, not a flask, a funnel over here. A filter funnel would work great. It would allow you to pour solution easily without any spilling. Moving on. Now, when we move on, my bad. So when we move on, the next step we see is that we add a few drops of phenolphthalein indicator, not into this whole system, but directly into the flask. You can use phenolphthalein, you can use methyl orange, you can use methyl red, you can use any indicator you like to, but we tend to work with the indicators that show a maximum of three colors, one for acidic, one for alkaline, one for neutral. We usually try not to go with universal indicator since it can show so many colored shades that it would be difficult to decide the endpoint. So as um, I think the universal indicator might attract you for its lots of colors and rainbow imitation, but it's a little bit impractical in lab at this stage. So add sodium hydroxide drop by drop by opening up this tab at the bottom and do the experiment until the indicator changes color. As soon as it does, notice the reading. Now, when a single person is doing this experiment, we ask the person to use all of its possible senses and resources. Now, if you're a right-handed person, I insist that you have your right hand on this tab so as to open and close the tab. You have your left hand over here so that you can keep shaking the bottle, but make sure you don't shake it that you break this very mouth of burette. They should not collide with one another because glass utensils can easily break. So let's be a little bit careful. With the left hand, keep shaking the flask. With the right hand, keep handling the tap. And your eyes should be right over here at the level. So your eyes should be right here at the level of this. You shouldn't be watching it from here if it's too high. You shouldn't be watching it over here if it's too low. This way, you're definitely going to end up with error. So even if you have to fold your knees and even if you have to readjust this clamp to bring this to equal to your height, that's a very good way.
Mhm.
And that way you never get an error. I hope you understand that part since your teacher has demonstrated this right in front of you. So I hope you get the idea how to use all possible resources or sensors. When you take the final reading in the burette, when the color changes, in this case, phenolphthalein, we do understand it changes from colorless to pale pink. It is colorless in both acidic and neutral medium. However, as soon as the medium gets alkaline, it changes to pale pink. And this can happen even when you add 1 or 2 drops of extra alkali. Okay? With higher
Mhm.
concentration, only 1 drop can bring a huge difference. So, clarifying this, let's go with the paragraphs we have. Calculations involving titrations are discussed in chapter 6. So, we are not going to discuss the calculations over here. The alkali is added to the acid from the burette until the indicator changes color. We already know that. We usually do a rough titration first. This gives us an approximate idea how much alkali will be required in terms of cubic centimeter to neutralize the acid. Imagine we found out that we require 22.50 cubic centimeter of alkali in the rough titration, right? So
Mhm.
when we do the experiment again, we'll be running in about 18 or 20 cubic centimeter of alkali quite quickly, swirling the conical flask left and right all the time to mix the solutions. Then we add the alkali very slowly for the next 5 cubic centimeter, whatever that we are going to use. 1 drop after another, because even if we do use 1 drop extra, it would change the color and it would change the neutralization point or the accuracy of result by a much bigger amount. So make sure you don't even use a drop extra on top of it. When reading a bureau test, it's important to remember that the numbers increase from top to bottom, or even if they don't, even if the paper is trying to confuse you, remember you go from a smaller value to a bigger value, right? Whether they are in
Yeah.
ascending order or descending order, it doesn't really matter. Okay. Now they are giving us a very good idea of the before and after readings for this one. Now, if I clear this up, you can see the before reading tells us that we have 2.10 exactly in the before reading. I hope you understand how am I counting it at 2. The longer line is 2, this is 2.1, and since the line exactly falls on 2.1, to make sure that it is accurate, we add 0 to it up to 2 decimal places, our answer comes out. In the after reading, if you see, this is 23, this one is 23, so 1, 2, 3, 4, and this line is 5, 6, 7, 8, and it is in between 8 and 9, so it's 23.8, and since it's in between 5. Remember to use 0 or 5 as your second decimal point value and know the numbers. You can't really predict a number in between. You can't write 8, 7 or 8, 8. That's not how it works. So 0 if it's exactly on the line, 5 if it's in between the line, and know the numbers. That's how you go up to the second decimal place. I hope this gives you the idea how that works.
Yeah.
Now, 2.10, 2.85, as I've said earlier, when you subtract them, you get the volume of alkali used. So 21.75 cubic centimeter is the volume of alkali used. After this, there is an entire set of calculations that we have taught back in chapter 6, but since you have skipped that chapter, you wouldn't know how to proceed with this. So let's stop right here. You don't know how to proceed with the calculations. Once we'll understand it, you'll know how to do it. Other indicators can also be used, such as methyl orange. Remember, methyl orange is orange in neutral medium, red in acidic medium, and yellow in alkaline medium, right? So,
Mhm.
if you were supposed to use methyl orange and put a few drops in the flask, they would immediately turn red because we had acid in the flask. And if you go with the exact neutralization point, that red would turn to orange. If you accidentally would have used a little bit of extra alkali from this burette, it might have turned from orange to yellow. So at first it was red. If you do it correctly, it would turn to orange. If you do it incorrectly, it might turn to yellow, giving you the idea that you have used a little bit of excess of your alkali. We don't
Mhm.
use universal indicator because it has a range of colors and changes gradually between them. We will never be able to see the clear endpoint. Endpoint is the point at which the indicator changes color, right? The point at
Mhm.
which the indicator changes color does not necessarily indicate the point at which the solution is neutral. This is the endpoint of the titration. It doesn't mean the exact pH at that point is 7. The pH changes very rapidly near the endpoint, and in some titration, even an extra drop more, or a drop less, which they change the pH from about 3 to 11. So there can be a step of 5 to 6 points of pH jump with just one extra drop. So predicting if the color was orange, that the exact pH is 7 is a poor claim. So never do that. It's the endpoint of the titration, and you have probably neutralized all the acid or all the alkali you had, but never think it's exactly at 7 pH. That's not how it works. Keep this point in mind. And this completes our topic for today.